Somewhere in the constellation Fornax, in a tiny patch of sky you could cover with a grain of sand held at arm's length, there are 6 galaxies that should not exist. Not galaxies that are unusual, not galaxies that are hard to explain. Galaxies that, according to the mathematics underpinning modern cosmology, the equations used to calculate the age, size, and evolution of the entire observable universe simply should not have had enough time to form. And yet, there they are, sitting in the data, captured by the most powerful telescope humanity has ever built, fully formed, fully massive, existing at a point in cosmic history when the universe itself was barely 500 million years old, a toddler by cosmic standards. When astronomers ran the numbers on what they were looking at, the conclusion published in the journal Nature Astronomy was not phrased cautiously. If these masses and these distances hold up, the paper stated plainly, fundamental changes to the reigning model of cosmology could be needed. Not a footnote, not a curiosity, a fundamental challenge to the framework that has explained the structure of the universe for nearly 30 years. This is the story of what the James Webb Space Telescope actually found, why some scientists are using words like impossible and crisis to describe it, and why the honest answer to whether physics itself has been broken is far stranger and far more interesting than any headline you have already seen. Let's start with what the standard model of cosmology actually predicts, because you need to understand the rule before you can understand why breaking it would matter so much. For nearly 3 decades, the dominant framework describing how the universe grew from the aftermath of the Big Bang into the galaxies, stars, and planets we see today has been something astronomers call the lambda cold dark matter model, usually shortened to lambda CDM. It is not a fringe theory. It is the closest thing cosmology has to a settled consensus, built from decades of observations of the cosmic microwave background, the large-scale structure of galaxy clusters, and the expansion rate of the universe itself. And one of its core predictions is deceptively simple. Galaxy formation is hierarchical. Small structures form first. Tiny clumps of gas and dark matter collapsing under gravity in the early universe, and then, slowly, over enormous stretches of time, those small structures merge and grow into the large, massive, well-organized galaxies we see around us today, including our own Milky Way. Crucially, this process takes time, serious amounts of time. Building a galaxy. The size and mass of the Milky Way is supposed to take billions of years of gradual merging and accumulation. That is the rule the James Webb Space Telescope was never supposed to break. And then it started finding galaxies that broke it anyway. The James Webb Space Telescope launched on December 25, 2021, and began full science operations in the middle of 2022. Its entire design purpose, the reason NASA and its international partners spent decades and billions of dollars building an infrared observatory the size of a tennis court and folding it into a rocket, was to look further back in cosmic time than any instrument before it, to catch light that has been traveling toward Earth for over 13 billion years, light emitted by the very first generations of galaxies that formed after the Big Bang. Nobody was surprised that Webb would find early galaxies. That was the entire point of the mission. What surprised almost everyone within the very first year of observations was what those early galaxies actually looked like. In 2023, a team led by astronomer Ivo Labbé published findings describing a population of red, massive galaxies that had formed roughly 600 million years after the Big Bang, meaning the light Webb captured had been traveling toward us for more than 13 billion years. That alone was not the shocking part. Finding galaxies that far back was expected. The shocking part was their mass. These galaxies contained stellar masses exceeding 10 billion times the mass of our Sun, an enormous, almost unbelievable amount of stellar material to have accumulated in such a short window of cosmic history. If the standard model were correct, galaxies this young simply should not have had time to build up that much mass. The universe, according to lambda CDM, had not yet had the billions of years of gradual hierarchical merging that this level of stellar mass was supposed to require. The reaction from the cosmology community was not uniform excitement. It was, and continues to be, genuine scientific tension. Mike Boylan-Colchin, an astronomer at the University of Texas at Austin, examined 6 of the earliest and most massive galaxy candidates Webb had identified, and found that they stood in direct contradiction to the prevailing model of cosmology, the same dark energy and cold, dark matter paradigm that has guided the field since the late 1990s. His analysis, published in Nature Astronomy, laid out the problem in stark terms. If these galaxies really are as massive and as old as the data suggests, the standard model itself may need fundamental revision. Here is where most videos on this topic go wrong, and where this one is going to slow down and actually walk through what scientists are considering, because the real answer is far more interesting than a simple declaration that physics has been broken. There are several competing explanations for what Webb is actually seeing, and serious researchers disagree about which one or which combination is correct. The first possibility, and the one many astrophysicists currently consider most likely, is that early star formation in the young universe was simply far more efficient than existing models account for. In this explanation, the fundamental laws of physics and the broad structure of lambda CDM remain intact. But the specific process by which gas collapses into stars during the earliest cosmic epochs happened faster and more effectively than anyone had modeled. Under the right conditions, with dense concentrations of primordial gas and less interference from the kind of feedback processes that slow star formation in the modern universe, galaxies could theoretically build up stellar mass at a dramatically accelerated rate. This would not require rewriting physics. It would require rewriting our understanding of star formation efficiency during a specific, extremely early window of cosmic history that no instrument before Webb had ever been able to directly observe. The second possibility is more exotic. Some researchers have proposed that dark matter behaved differently in the early universe than standard models assume, potentially clustering or interacting in ways that catalyzed the formation of large structures faster than gravity alone, acting on ordinary matter, would allow. This explanation edges closer to requiring genuine revisions to particle physics, since it implies dark matter, whatever it actually is, may have properties beyond the simple cold, slow-moving, weakly interacting particle that current models assume. The third possibility, favored by a smaller but vocal group of researchers, is the most dramatic. It suggests that the timeline itself, the underlying relationship between redshift, distance, and the age of the universe that all of these calculations depend on, may need adjustment, potentially involving changes to how we understand the cosmological constant or the nature of dark energy. Or this is the version of the story that gets closest to what a headline might call breaking physics, because it does not simply ask whether stars formed faster. It asks whether some of our basic assumptions about the age and expansion of the universe itself are subtly wrong. None of these three explanations has become the accepted consensus. That is not a failure of the science. That is exactly what science is supposed to look like when it runs into something genuinely unexpected. And there's a fourth possibility that responsible researchers keep front and center specifically because it is the least exciting and therefore the easiest to overlook, and that is the possibility of measurement error. Determining the mass and precise distance of a galaxy over 13 billion light years away is an extraordinarily difficult technical challenge, involving careful modeling of exactly how much of the light Webb detects is coming from stars versus dust versus the glow of actively feeding black holes at a galaxy's center. Researchers, using a massive cosmological simulation called UCHU, built from over 2 trillion particles, have argued that the stellar mass to light ratios reported for some of these early galaxy candidates could not have realistically been as high as claimed, suggesting the true masses may be lower than the original headline-grabbing numbers implied. Other astronomers, examining the same population of galaxies, have found that a portion of their apparent brightness likely comes not from an implausibly large number of stars, but from actively growing supermassive black holes at their centers, sources of light that can mimic the signature of a much more massive, mature galaxy, if not properly accounted for in the analysis. This is the actual texture of what is happening in cosmology right now, in the middle of 2026, nearly 4 years into Webb's science mission. It is not a single dramatic discovery that instantly overturned everything scientists believed. It is a slow, escalating, genuinely contested argument playing out across dozens of peer-reviewed papers, with some of the most respected researchers in the field landing on completely different sides of the same question, and with the observational evidence itself still being refined, reanalyzed, and debated in real time. And the galaxies are not the only piece of this puzzle. In 2026, astronomers studying an object called XLSSC 122, an enormous galaxy cluster observed by Webb at a staggering distance, found something that deepened the mystery rather than resolving it. Galaxy clusters are the largest gravitationally bound structures in the universe, requiring vast quantities of dark matter, hot gas, and hundreds or thousands of individual galaxies to accumulate across truly enormous scales. On a process the standard model says should take an extraordinarily long time to complete. XLSSC 122 was not simply massive. It was massive enough to produce strong gravitational lensing, meaning enough matter had already collected in precisely the right configuration to visibly bend and magnify the light of galaxies sitting even further behind it, an effect that requires a genuinely staggering concentration of mass. Finding a structure like that so early in cosmic history raised the exact same uncomfortable question the individual impossible galaxies had already raised. Did massive structures form more efficiently in the early universe than any model currently predicts? Is this particular cluster simply a rare, unusually concentrated outlier produced by an unusual merger history? Or is something more fundamental about how astronomers currently model the growth of the largest structures in the universe simply incomplete? It is worth pausing here, because this is exactly the point in the story where the discipline of good science reporting matters most, and where the discipline of clickbait tends to abandon it entirely. One researcher, studying the XLSSC 122 findings, put it about as clearly as anyone in the field has. The interesting question, they argued, is not whether this discovery breaks cosmology. The answer to that specific framing is no. The far more interesting and far more accurate question is whether Webb is revealing that the early universe built its largest structures through a process that current simulations have not yet correctly captured, which is an entirely different and much more scientifically productive question than a simple, dramatic claim that the laws of physics themselves have failed. So, has James Webb broken physics? No. Nothing about the laws of gravity, thermodynamics, or the standard model of particle physics has been shown to be wrong. What Webb has actually done is something arguably more valuable than breaking physics, and considerably harder to compress into a 6-word headline. It has taken a period of cosmic history that was previously invisible to us, the first few hundred million years after the Big Bang, less than 3% of the universe's current age, and made it observable, measurable, and arguable for the very first time. Before Webb dipped, astronomers were extrapolating backward from what they could see in the relatively nearby, well-studied universe, building models of the early cosmos based on inference and theory rather than direct observation. Webb changed that. It gave scientists actual data, actual galaxies, actual light that traveled for over 13 billion years to reach a mirror assembled from 18 hexagonal gold-coated segments floating nearly 1 million miles from Earth. And that actual data does not match the predictions cleanly. That mismatch is not a failure of physics. It is physics doing exactly what it is supposed to do when new, more precise instruments finally look somewhere nobody could look before. Old models get tested against new evidence, and when the evidence does not fit, the model has to change, not the universe. This is precisely the same pattern that has played out again and again throughout the history of astronomy. And it is worth remembering that pattern before assuming Webb's early galaxies represent some unprecedented crisis. When the Hubble Space Telescope first captured its deep field images in the 1990s, revealing thousands of previously unseen galaxies in what looked like an empty patch of sky, it did not confirm existing predictions cleanly either. It forced revisions. When astronomers first measured the accelerating expansion of the universe in the late 1990s, the finding that eventually won its discoverers a Nobel Prize, it directly contradicted what most cosmologists at the time expected the universe to be doing, and it forced the introduction of dark energy into the standard model in the first place. Each of these moments felt in the years immediately following the discovery, like a genuine crisis for cosmology. Each of them eventually led not to physics being broken, but to physics being refined, expanded, and made more accurate. The impossible early galaxies problem may follow exactly that same trajectory, resolved eventually by a better understanding of early star formation efficiency, or by more careful accounting for black hole contamination and brightness measurements, or, if the more dramatic explanations hold up under further scrutiny, by a genuine and historic revision to how cosmologists model the timeline of the early universe itself. What makes this moment in 2226 genuinely remarkable is not that the answer has been found. It is that the disagreement is happening at all out in the open, in real time, across dozens of competing papers, precisely because Webb has finally given the field enough real data to argue about. For decades, questions about the first few hundred million years of cosmic history were the domain of theoretical speculation. Models built on models, extrapolations stacked on extrapolations, with no way to directly check any of it against reality. Webb ended that. It is currently projected to have enough fuel remaining for at least 20 years of continued science operations, meaning the observatory currently generating this entire controversy is nowhere close to finished. More galaxy candidates are being identified. More spectroscopic follow-up observations, the kind of detailed measurements that confirm a galaxy's true distance and composition rather than relying on rougher estimates, are underway right now through projects like CosmosWeb, a survey covering an area roughly 50 times larger than earlier deep field studies, specifically designed to hunt for the rarest, most massive galaxies in the earliest slice of cosmic time science has ever been able to examine. So here is where this genuinely stands, right now in the middle of 2026. The James Webb Space Telescope has not broken physics, but it has done something almost as significant and considerably harder to overstate honestly. It has exposed a real, unresolved, actively contested gap between what our best theoretical models of the early universe predicted and what actually happened in the first few hundred million years after the Big Bang. Serious scientists at serious institutions disagree, in published, peer-reviewed literature about whether that gap will be closed by refining our understanding of star formation, by rethinking the behavior of dark matter, or by something more fundamental about the timeline of the cosmos itself. Nobody currently knows which explanation is correct, and anyone claiming otherwise, in either direction, is telling you more than the data currently supports. What we do know is this: a telescope built to look further back in time than any instrument in human history has done exactly that, and what it found back there does not fit neatly into the boxes we built for it in advance. That is not the universe breaking. That is the universe, for the first time, actually being watched closely enough to argue about. And somewhere out there, in the light still arriving from galaxies that formed when the cosmos was younger than 3% of its current age, the answer to exactly how those structures grew so large so fast is sitting in data that scientists are still, right now, in observatories and universities across the planet, working to fully understand. If this is the kind of story you want more of, the real science behind the headlines, explained honestly instead of oversold, subscribe and stay close, because Webb is not finished looking, and neither are we.